All right, with that, it's a great pleasure to have Thierry here. Thierry was actually a Ph.D. student at University of Washington. And Thierry probably does not remember this and know about this, but the first time I actually ever met Thierry was actually at NASPOS conference at in Atlanta, Georgia, where it was, I think, yeah, it was a workshop that we were in. I think this was when Luis was still doing all the approximate computing stuff, Thierry, if you remember.
Yeah,
You were
yeah.
next to him, and I was like, and then Luis was like, "Oh, you should meet Thierry." He's like, he's actually starting his PhD. So this was quite a while back. But it's really exciting to see how far you've come. It's super exciting to hear about the OctoML work that you're doing. I think if you can help the students understand some of like the nuances about like why do you need frameworks like OctoML, like fundamentally, right? Like why is it so important? You know, we've focused so much on kind of the mechanics of doing stuff, but how you accelerate that whole pipe is actually critical as well, right? I think that's one of the key things, at least I see, that OctoML is doing, in addition to all the hard work of getting stuff running. So if you can kind of emphasize some of those practical standpoints that you have experienced through them, that'd be awesome. With that, I'll turn it over to you. And thank you so much for waking up early.
Yeah, my pleasure. I cannot emphasize how much I would have loved to take a class like this when I was a grad student. So what you're up to is, putting this content together, I think it's really great. And I feel very envious of all the students taking this class right now. So yeah, it's a great pleasure to present today. I will share my screen, make sure you can see the slides. Can you all see the slides now?
Yeah.
Let's see. All right, great. So yeah, it's a great pleasure. Thank you for the introduction. And the topic of today is to talk about TVM. We have a whole 45-minute budget, I believe. And what I'm hoping is that by the end of this talk, you'll get a solid understanding, a solid grounding and understanding what uses you can get out of TVM. So what kind of users have TVM been built for? What is the secret sauce? What is happening under the hood to make TVM work the way it does? And I'll talk about some exciting initial work we've done on microcontrollers in the TinyML space that is in progress, but that is looking very promising. So I'll start with the simplest view on machine learning deployments, and this is something that by now you're already well familiar with, having taken this class. But let's say you're asked to deploy a classifier that can classify images, something like a ResNet, for instance. Typically, you have to do this two-step process of training, right? You have to train this classifier, and then you have to deploy for inference. Now, I'm not going to talk about training today because this is off topic. I'm sure you've already learned a little bit about this. There's the process of taking a labeled data set, defining a model. This model has parameters that are fine-tuned and trained via backpropagation on a lot of GPU machine. And over time, the accuracy of this classifier goes up. And finally, you have something ready to deploy. So I'm not going to talk about training today. What I'm going to talk about, I forgot to mention that this is also done inside of a deep learning framework. So your PyTorch, TensorFlow, MXNet, these are tools, standard tools that have really helped machine learning practitioners in these tasks. 5 years ago, 6 years ago, it was very tedious to get a model up and running and trained. Now you can do it in just a few lines of code. So these frameworks are very important, and this is where you train your network. But now, what do you do with deployment? And I'm going to talk about this. TVM right now, as it is mostly about deploying your network. Now that it's been trained, what do you do with it? How can you deploy it on different platforms? How can you get it to run fast? And when you're asked to deploy a model, typically you have to answer multiple questions. For instance, what are you deploying your model on, right? The machine you trained your model on might not be the machine you deploy it on, right? So we're talking about CPUs, GPUs, DSPs, FPGAs, accelerators. It could be on the edge, it can be in the cloud. And edge has, a whole spectrum. Are we talking about a laptop, a smartphone, a tiny little device? And also, you might be able to, at deployment time, make some accuracy and efficiency trade-offs, right? Going back to the approximate computing days, this was a central idea that you could get things to run faster. And now with machine learning, we're seeing this being used with quantization techniques, sparse optimizations, et cetera. And finally, you also have to think about what you're deploying your application in, right? Is it some sort of Python program? Are you talking about C++ or C? Is it inside of what operating system is it running inside of? Or, is it just running on bare metal? There's a lot of edge devices that might not have a lot of operating system capabilities. So really, you have to navigate all these choices. And I cannot emphasize how challenging this is, because when you're asked to take a model and deploy it somewhere, well, first of all, you need to figure out, well, where is this model coming from, right? Did you train in PyTorch, TensorFlow, MXNet? Has it been exported to an intermediate format like ONNX, or maybe TensorFlow Lite for edge deployment? And what machine are you deploying this on? And to navigate every single combination of where your model is coming from and where you're deploying it onto is very challenging. You essentially have, based on the case study, based on the scenario, you might have to use different tools. And this is what makes a big, it's a cause of a big headache for a lot of machine learning practitioners. So for instance, if you're asked to deploy a TensorFlow Lite model on an ARM processor, you're in luck. There's a really nice TensorFlow Lite interpreter that's been nicely packaged. You can deploy it easily. And so, you can be done in a couple hours. Now, if you get the model from PyTorch, you might have to go through extra hoops, right? Now, there are open source forks of PyTorch that will work on, say, ARM processors, or you might have to export the model in some format and into TensorFlow and then into TensorFlow Lite. Or you might have to define your model and retrain it from scratch. But you can imagine for every one of those combinations, you might have to resort to different solutions. So in order to alleviate some of that pain, TVM is really, you can see it as this universal compiler that will essentially ingest models from different frameworks, PyTorch, TensorFlow, MXNet, or the ONNX format. And it can, via the use of different code generation backends, it can target different types of devices, CPUs, GPUs, you name it. And the key is something that I'm going to, explore in a few slides. But if you can think of TVM in just one sentence, it's essentially this end-to-end deep learning compilation stack. The reason why it was called TVM is because we wanted to mimic the success of LLVM that made a big impact in the compilation space, because it could ingest different languages like C, C++, OpenCL, and then via a unified IR and a common optimization framework could target different hardware backends. And so that was a very powerful idea. We wanted to do something similar, but for deep learning, which requires you to think at a very different level of abstraction. So just to point out something that may not be obvious, but TVM is a fully open source project. It's under Apache incubation. And based on the Apache governance model, it's community owned. So that means it's not really under the control or leadership of a single corporate entity, which has a lot of its appeal to many users, both in industry and academia. We're getting close to 500 active contributors and up to 6,000 stars. And this project started about 3 years ago. So it's been really exciting to see this project grow and reach the size that it's at today.
Jerry, I have a question. So when you started writing this stuff, right, what was the general motivation? I understand what TVM does today kind of thing, but there's often like a certain seed, right? Because it's a pretty big project that, it's become a very big thing, but I'm trying to, I'm trying to date it back to that original seed.
Yeah, so there were multiple things. So Tianchi was the lead author behind TVM, and I started collaborating with him very early on. The lead motivation at the time was that Tianchi at the time was a researcher working on deep learning systems, and specifically MXNet, and they realized that they couldn't solely rely on essentially invoking external libraries like MKLDNN or cuDNN to reach really good performance, and they wanted to explore other approaches like code generation that would give them more flexibility to get as much performance as possible on a hardware backend. So one of the things they wanted to do was, for instance, code fusion. And at the time, it was a fairly novel idea. For instance, TensorFlow XLA allowed some code fusion capability. And but he wanted to rethink how you would tackle this problem of doing code fusion with a very flexible code generator based on essentially the work that Halide was back in the day. So really, it was about taking performance to the next level by essentially combining graph level optimization and operator level optimization. And when I jumped onto the project, I was a hardware architect, and I was interested in making hardware architectures programmable. So when I first talked to Tianxi about his project, I was like, could we also use this compiler that you're building that is meant to target CPUs and GPUs? And can we also think about what it would take to target specialized architectures? And so it kind of started from this motivation to get as much performance out of different types of hardware, but also be future-proof in the sense that you could target new architectures down the road. And so I'm going to try to touch on some of those things in my talk, and hopefully convey the point across. But that's a really good question. I think it was driven from having worked on those frameworks, like having built something like MXNet and thinking, well, we're hitting a wall in terms of the performance that people want to get. Like, how can we push it further? And then there was this convergence of research collaborations that was like, hey, now that you're building a new complete stack, what would it take to change things so we could target new designs? Those accelerators that people are talking about, someone's going to have to program them. So it was kind of the right initiative at the right time that led to this project that really blew up. Yeah. So I'm going to take a couple minutes to talk about what problems TVM addresses before I kind of go into the details, because I really want to hammer on what kind of problems TVM can solve. And I'm going to center this around 3 points, right? The first question of portability, right? Now that you've trained a network, how can you deploy it on different kinds of devices, right? And what challenges are you going to face there? We're also going to talk about efficiency, right? Because TVM is known to really get a lot of efficiency out of your hardware. How does it do that? Well, I'm going to try to motivate this first. And then finally, there's this question of software support. And this mostly for the hardware folks, the hardware architects. We love building hardware, but when it comes to programming this kind of hardware, it's a whole other story, right? And we often overlook this. We love to look at gigaflops, teraflops, but making it programmable, that's a whole other story. So I'm going to try to present 3 motivations with 3 different use cases. So here's my colleague Mehrdad Hassar. He's a brilliant Ph.D. Researcher at University of Washington, and essentially he's got this model from TensorFlow. It's keyword spotting model that essentially does wake word detection. Think of your Siri or Alexa, always on listening for keywords, and deploying this on an interesting platform called the Azure Sphere. So it's Microsoft Secure Edge IoT device. And really, it's a heavily constrained target, right? There's limited SRAM and flash budgets, very bare bones operating system. For instance, you cannot compile C++ code. That's a no-go. There's things like no dynamic linking. So, when it comes to deploying a model onto a platform like this, you have to really put a lot of effort to get the model running. So, for folks like ML engineers that design really great models that run just fine on x86 or on CUDA GPUs, if they ever need to move and deploy this network onto something that becomes a bit of a challenge, now they're kind of on their own. And this is mostly because most of these frameworks are designed for, your common development machine. And so this is a big challenge. And so TVM here will provide the ability to deploy ML thanks to a lot of different code generation backends on platforms where it would typically be very painstakingly difficult to get your model deployed. So I'm going to touch a little bit on this later on in this talk. The second motivation for TVM is to get as much efficiency out of your target system. So I'm going to talk about some work that is done by some really brilliant Facebook engineers in Facebook AI. And so they were dealing with this wave RNN model for speech synthesis, and they wanted to essentially get really high throughput. When they run their model on PyTorch, and this is on x86, right? They're running it in servers. It runs. It's supported, right? So there's not the problem that you had before, where my colleague Mehrdad, had to figure out a way to deploy the model. It runs, but it's very slow. They have this 3 millisecond runtime, and to run it in real time, they had to make it run 100 times faster. So how are you going to do this? Well, this is a very specific use case done by really talented engineers. But essentially, by adding successive optimizations in TVM, so first of all, they import the model from PyTorch into TVM, apply some auto tuning, and then they look at implementing different types of block sparse operators, right? So because you have these GRU layers and fully connected layers, you'll find there's a lot of sparsity that you can take advantage of. So they implement block sparse kernels, then they apply type conversions to use, 16-bit BF data types. And then, they add extra layers of optimizations. And at the end, they get about 100x speed up in about a week of engineering. Now, mind you, those are really, really talented folks. But essentially, TVM is a framework where you can implement these kind of optimizations in a fairly short turnaround time. And when you're Facebook and you're running a lot of AI in the data center, this is huge in terms of data center cost savings, right? And there's a whole talk about this work. It's really impressive. And as a bonus, because they were able to optimize the hell out of this model, they could actually deploy on smartphones and running in real time. So that was a nice bonus added to all this work. And so this is targeting really the ML sys engineers. So people who also have a good systems background, who are used to doing a lot of deep, low-level optimizations. And every millisecond or microsecond that they shave off from inference results in a lot of monetary gains. So it's very important. And most frameworks are relying on libraries that are optimized for the common workload, right? So you can imagine that you have these workloads that are often benchmarked, and that is driving the decisions on how a certain library should be implemented. And also, frameworks rely on, for instance, inefficient interpreters. When they did some profiling, they saw, every time you invoked an op in PyTorch, it was a 1 to 2 microsecond overhead. So they did the math and they're like, oh, no, that's not going to work out given our target. So we have to think outside the box. And what's nice about TVM is that it provides a lot of optimization capabilities, but also allows you to deploy the model in a very, bare bones package that's going to minimize a lot of overheads that you typically have in other interpreters, for instance. And then finally, the last motivation I'll talk about is TVM for software support. And this is for my hardware architect colleagues. And, we know there's a lot of work done on building new accelerators coming from a lot of companies and a lot of startups, right? It's really a golden age, a golden era of building AI chips. And, you probably have hundreds of companies building silicon there. And really the challenge there is, well, how can you build a software stack? And there's a lot of questions that you need to navigate here because, do you build, for instance, a backend to TensorFlow via XLA? Do you build a backend for PyTorch via Glow or TorchScript? Do you add another execution provider to NX runtime? The machine learning engineers, they want simplicity. So they're going to use these frameworks. And if you don't provide a hook, they're not going to use your hardware. So it's very challenging to navigate these choices. And so, TVM can alleviate a lot of this pain by essentially providing a shortcut for model deployments. TVM has the layered abstractions you can rely on to integrate external hardware code generators or external libraries optimized for your hardware. And we're seeing companies like AWS, Xilinx, ARM use TVM to target their accelerators. And so there's certainly success stories there. And I wanted to touch on the impact on industry before I go into the technical details. But TVM is used today by a lot of really important companies, right? For AWS, Alexa model was optimized using TVM. So that's machine learning on the edge. For Facebook and Microsoft, they've done a lot of optimization for their data center, and they've gotten really good results. Qualcomm is a hardware vendor that has a DSP, and actually I saw it's in your schedule for this TinyML class. So I saw that you have a whole section on accelerators, ARM, NPU, Qualcomm DSP, and these are things that TVM supports or is on the way of supporting. So we're working closely with Qualcomm, with ARM on supporting these accelerators. So it's really it has a lot of options for for plugging in a lot of different backends. So now you probably want to know how it works, right? And so I'm going to talk about the TVM stack, and we're going to do a bit of a deep dive. But there's a lot to talk about. We can have a whole day seminar on TVM or even a whole class on TVM. So I'm going to touch on different bits. This is the view of the stack that we have on our website. I just took it from there. And essentially, if you start from the top all the way down to the bottom, you have importers that will take models from TensorFlow, PyTorch, etc., and will convert it into an intermediate representation called relay. And you can see that TVM relies on essentially an unified IR that essentially can define high-level compute graphs. You can think of these as the graph representation of your model. And there's also a lower level instantiation of this IR that is used to represent tensor programs, so operator definitions. And so via this multi-stage lowering, you can finally target some backends, which is what you see all the way at the bottom. So LLVM, C code generation. If you're targeting GPUs, you have CUDA code generation, Metal, OpenCL, Vulkan. And TVM comes packaged with also some very lightweight runtimes. So you can deploy it on the data center, on the edge. And finally, this targets a lot of different devices. So I'm going to touch on 4 topics today in this deep dive. I'm going to start with talking about operator level optimizations. And we're going to walk on different, about different points to finally conclude with how TVM supports microcontrollers. So let's dive right into how TVM optimizes programs at the operator level. So remember this image that we started with, this was a very simple classifier. And essentially, I'm going to try to dive into what this black box really is. And by now, you should already be familiar with what's happening under the hood, right? You have a model. And for instance, you can imagine a simple, feed-forward network that we use for classification, like a mobile net or a ResNet. It's essentially a sequence of operators, of layers that perform computation on input data, right? And this data is typically a tensor, which is a high dimensional array. So you'll have your input tensor, and you'll have a weight tensor or parameter tensor. And you're going to apply a mathematical or linear algebra operation on these tensors, like 2D convolution. And this will produce output data. So far, this is fairly straightforward. This operator has to run on a CPU or a GPU. So it's essentially a binary sequence that gets executed on your CPU. And you can think of writing an operator as a very simple task, right? For instance, matrix multiplication, you can write it in about a dozen lines of code. But in order to get the most performance out of your hardware, to get matrix multiplication running as fast as possible, we're talking about thousands of lines of code for this to run really, really well. And what do I mean by really, really well? I'm talking about orders of magnitude faster execution. So to get to this ninja level programming, you need to be very familiar with your hardware target. And it's really something that is generally written by extremely experienced, kernel engineers that have been doing this for years and years. To take a look at a real life example, I took a look yesterday at TensorFlow and TensorFlow-like kernels, and you can see that, for instance, we're looking at a depth-wise unsigned int, depth-wise convolution for 3x3 filters. And we have about a 13,000 line of code file and of expertly crafted code, right? That's going to give you really good performance. And why are there so many lines? Well, there's a lot of assembly inlining that you need to do in order to get a really fast performance on your hardware. And here specifically, I assume it was written for ARM CPUs. There might also be different implementations for your depth-wise convolution, right? You might have to account for different quantization types, different rounding modes. Your depth-wise convolution might have different axis strides, et cetera. So you might have to define slightly different variants of the same kernel. And also you might have to define implementations that take advantage of special hardware instructions like your Neon hardware intrinsics in ARM. So essentially you'd have to define multiple variants for that one operator. And you can imagine that in order to achieve this hand-tuned performance, that's going to be a lot of code, right? And one of the challenges we set out to answer was, how can we achieve this hand-tuned performance, while keeping code fairly compact and maintainable and readable? Because you can imagine that this was just a very narrow slice of all the operators that you need to support in a modern framework, right? You have all your layers like conf3d, conf2d transpose, et cetera. And each operator is typically take in different input tensor shapes, can use different dilation factors, stride values, padding sizes. And also hardware evolves, right? So if ARM comes up with a new set of vector instructions, you're going to have to maybe revise a lot of these low-level kernels to take advantage of those. So every year there's going to be new generation of Intel and ARM processors. So we're talking about a really large code maintenance challenge that you can imagine can result in a lot of bloat. So thankfully, there was this halide programming model that was introduced in the earlier half of the last decade, circa 2013, 2014. And halide introduced a really interesting notion of separation of the functional definition of your program and the schedule definition. And so I'm not myself a programming language person, so I'm just going to give you a very quick overview. But essentially, with the functional definition, what you're defining is what this function is doing, all right? Just from a purely mathematical standpoint. So for instance, when you think of a Gaussian blur or some blur algorithm, you can define what the blur function is doing based on, let's say, every index of your output array is essentially this weighted average over 3 consecutive pixels, right? And how this output image is computed is really something that you have the freedom to do. And it's not going to change the correctness of your output. So we're all familiar with how caches work. So we know intuitively that, if you have an array, you're probably going to want to access it. You want to order the loops so that you're reading, every element in a row before you go to the next column. And you're not going to go read it backwards because you're not going to take advantage of cache locality. So the way we write programs is highly influenced by how we understand caches, how we understand processor architecture. But we do it in a way that we almost forget why we do it. And we'll see the difference in terms of performance, right? If you write the same blur program by inverting access in your array, you're going to have really slow performance. So this functional definition essentially is not, you'll see that there's no loops in the definition of this algorithm. And what will materialize the program that gets generated is the schedule definition. So the schedule definition defines how you implement that function. And for instance, it will define the loop ordering. It will add extra details on whether or not you want to take advantage of vectorization and parallelization. So you can see that in those few lines, essentially, we're telling the program to apply tiling, to apply vectorization, and to take advantage of parallel cores. And all of this is done in just a few lines of code. And that was a very powerful idea that was used in the area of computer vision. Now, TVM relies on the same principle of separation of algorithm and schedule. And we're going to look at a matrix multiplication here because we're talking about deep learning, so we cannot avoid the topic of matrix multiplication. TVM has this tensor expression DSL. It's essentially a DSL that a human can write, and it defines the algorithm and a schedule. You can see here, for instance, that in one line, line C, we can define a matrix multiplication. And as you can see, there's no nested loops here. This looks very much like a mathematical definition in the sense that for every output element of your output matrix, you're performing a reduction over a reduction axis, K, right? And you're performing a multiplication across elements from A and B and performing reduction over that. So this algorithm definition is very compact. And then we can materialize the implementation by generating a schedule. And in this case, we're just going to generate a default schedule. We're not doing anything special about this. So this will generate a program in TIR. It's an internal IR in TVM that we use to represent programs, tensor programs. And this TIR itself can be lowered down to LLVMIR, to CUDA code, to C code, to OpenCL, etc. So it's kind of this universal IR that we then use to do code generation and code lowering to different backends. And so this looks a lot more like a program that you used to writing in C or Python. And you can see that there are 3 nested loops. And this is essentially your standard implementation of a matrix multiplication. Now we're going to do more fun changes to this schedule. So we're starting with a vanilla schedule, and we're going to apply tiling, which essentially means that you're going to chunk the computation. And why do you need to chunk it is because you can imagine that when you do matrix multiplication, your input arrays are going to be so big they're not going to fit into cache. And with matrix multiplication, you need to read the same element, the same lines multiple times, because for every line in matrix A, you need to perform multiplication across every column in matrix B. So there's a lot of rereading, and if you're performing, if the array is too large, you're going to spill in your cache, and your performance is going to be very slow. So you're going to chunk your matrix multiplication computation by applying tiling, and you can also split the reduction axis. So now you have really nice, smaller matrix multiplication chunks that you can compute. And now, as you're performing this matrix multiplication and as you're reaccessing data, you're going to stay within the confines of your cache and get much better cache hit rates. But your program is going to look a little uglier now because now you have 6 nested loops, right? So this is a fairly easy concept, and probably many of you have had to write programs like this to get better performance. And you can imagine you can add extra optimization. So here we're going to add vectorization, which eliminates the innermost loop because now we're applying vectorization on that axis. So essentially now we end up with 5 nested loops, and we're taking advantage of SIMD capabilities of your CPU. And so this is essentially what a Ninja programmer would do when writing a program. You're applying all these schedule transformations, and you can see after about 13 lines of schedule transformations, you end up with a program that's a lot uglier, that probably you wouldn't want to maintain and debug, but that's about 200 times faster.
I got a quick question for you, Thierry.
Yeah.
So on the previous one, so when you do the tiling, like, how do you know how to do the tiling? Did I miss that?
That's a great question. So I'm going to ask you to hold that thought, okay, but I'm going to try to address that. Yeah. Well, let's see. Right. So in tiling, so actually, I'm not showing the whole program, but I will point you to this very example in our tutorials on our website. But you can see that we're applying tiling factor BN, right? And that's going to define essentially how big the tile is along each dimension. And as a programmer, you have control over that. So you might say, like, I want to compute this matrix multiplication in chunks that are 256 by 256 because I know that's going to fit well in my L1. And so how does the programmer know that it's 256 instead of 128 or some other value? I'm going to touch on this. So typically, yeah. So as a summary, we get really good performance because we're able to apply tiling and loop permutations to get really good cache hit rates. We can apply array packing, which is a technique that essentially rearranges your input data to turn non-contiguous axis into a continuous axis pattern. We can take advantage of vectorization and thread level parallelization to use all the cores. Now, I'm going to try to address this question in the next phase of this talk, which is about auto scheduling. And so in the previous example, I showed this example that you can do yourself. You can get 200 orders of magnitude speed up over the naive implementation on an x86 CPU, but you're still slower than MKL, which is your Intel highly tuned library, right? We were able to do this in a few lines of code. Like, how could you take this a notch further? And the trick here is that, scheduling is a bit of an art and requires a lot of trial and error, right? So you're going to be a programmer in front of your computer. You're going to be able to compile programs and run them and measure them. And you're going to try to tweak the array, the tiling factors, how wide your vectorization factor should be, et cetera, loop orders, until you get really good performance. And, of course, you can work backwards from looking at the architecture specification, but, it's not that easy to derive one-to-one from just, let's say, the cache sizes of your CPU. So instead, rather than having a human do trial and error on trying different strategies, why not let ML dictate this search? Because it's a very large search for a single operator, like a conf2D optimized on a GPU. We're talking about billions of possible schedule optimization choices, right? This is a very large space. So can we let ML navigate this for us? And this is a question that my colleagues actually explored in this NeurIPS paper. So, you can imagine that you're starting with your algorithm definition, which in this representation is expression E, and you have schedules that you can templatize. And when you templatize these schedules, which means you're leaving some factors or reordering options as tuning parameters, you're defining a search space, right? And so you're feeding these into AutoTVM, which right now is like kind of a toolbox that will do automated exploration. And AutoTVM will try different optimization configurations. So it's going to try to fill in the blanks into the schedule template. And every time it fills the blank, you end up with a different program that's going to look very different from the one you tried last time. We have this code generation that will do code lawyering and produce a program that can run on hardware. So really, this automated search relies on real hardware. You need something that will execute the program. And in order to formalize this search or this optimization problem, you need to find the optimization configuration in this whole space that will minimize the runtime on that target hardware of the program that is generated from your expression and applying that optimization configuration to. So you're filling in the blanks and you're getting a valid program, right? So out of these billions of possibilities, there's one that will minimize execution time. I'm not going to go into details of this paper because that's a whole talk on using ML to optimize ML. But the key idea here is essentially we use a statistical cost model that essentially we train from feature that we extract from the generated program. Like, from that generated program, how many memory accesses are we doing? What are the size of the innermost loop or the outermost loop, et cetera? So it's learning features from there. And also it's getting data. It's getting the results of running these programs on the hardware. And so that was a very powerful approach because we were able to, for instance, at the time, outperform libraries like cuDNN on CUDA GPUs. Now, that's a pretty big deal, right? Because you're essentially beating NVIDIA in its own turf. Now, I will say that cuDNN is optimized for the average case, right? And for instance, we found out at the time that, hey, cuDNN has really good libraries for batch inference on GPUs, but single batch wasn't that good. So we're able to easily outperform it. And really, this is the key idea that I wanted you to get out of TVM is that it's optimization for your one model running on your one hardware, right? So this is essentially bespoke optimization for your one deployment. And cuDNN is great for the average case. You need something running right away quickly. It's going to give you the performance you need. But if you need to auto-tune it and get the extra mile, TVM is really good for that. So I'm going to shift gears now that I've talked about automated search. And I'm going to try to touch on graph level optimizations, right? So far we've talked about how to optimize individual kernels, right, at conf2D. Now, how do you optimize the whole graph? This is another lengthy topic. My colleague Jared Roche had a paper on Relay that introduced this programming language. It's a functional programming language. It's statically typed. And we use it as an IR to represent machine learning workloads. So you can imagine a program where instead of add or multiply, you have convolution or ReLU, right? And what was really neat with Relay is that it was written by a programming language person, by a compiler person. So they said essentially any machine learning program or any machine learning workload can be viewed as a program. And the kind of features you see in an ML framework, like applying quantization or applying shape inference, can be seen as standard optimization passes, the same way you implement an LLVM optimization pass for LLVM IR. So I'm going to look at a couple examples here. Operator fusion, which I mentioned at the very early beginning, motivated the use of TVM, and quantization. I'm going to go quickly over these. So operator fusion is a common technique used nowadays by a lot of frameworks. And the idea is fairly straightforward. So we're zooming in on a network and we're seeing the succession of 3 different operators that you'll see a lot in vision models, right? You have a conf2D, a batch norm, and a ReLU. And every time you're producing intermediate data, and you can imagine that if you're invoking a library, a BLAST library, well, you need to call a function and write the output to an array that you've allocated. And every time you perform computation, well, this is putting a lot of strain on off-chip memory access, right? Because we're talking about fairly large tensors. And from a systems perspective, this is bad, because if you look at the succession of these ops, turns out, do you really need to store everything into an array and then perform ReLU? Because we know that ReLU is essentially a very simple mathematical operation that just clips your values. And maybe you can do this inside of your conf2d, right? Or inside the previous operator. So this is what Fusion really is about. It's about combining operators so that you don't have to do as much DRAM. You don't have to use as much or perform accesses to DRAM in between when it is possible, because there are, of course, rules to applying Fusion between operators. So with Fusion, you end up with a fused kernel that essentially is conf2d, bash norm, and ReLU all in one. And now you have a lot less DRAM accesses, right? And in order to perform this kind of fusion, now you need to rely on a augmented operator library, because if, let's say, your graph compiler says, hey, there's this conf2d and this ReLU that I'd like to fuse. Do you have an operator that implements this? And if you don't, then you cannot apply this fusion. So as someone who implements the library, you need to extend your library. And so we're talking about an explosion of operator implementations. And thankfully, with code generation approaches like the one of TVM, we have a flexible way to fuse it. Because if you remember, we had this tensor level IR, we have these programs, and we can essentially apply fusion rules so that we can move, things like ReLU into, the innermost loop of your conf2d implementation. And this will result in really nice performance gains. Now, I mentioned, Relay is essentially a compiler optimization path, a compiler optimization framework for machine learning programs, right? And you can think of Relay as essentially as the equivalent of LLVM for machine learning programs. And just like LLVM, you have different optimization levels. Each optimization levels will add a whole bunch of extra compiler passes when you compile your program. And so, with Relay, we're able to experiment with different types of program optimizations, like doing operator fusion, constant folding, common sub-expression elimination, and overall get better performance because we're massaging your machine learning workload at the graph level. And this combines really well with the lower level code generation approach that I discussed previously, and can produce really good results. There's also work that has been done on automated quantization, and I'll go over it very quickly. But again, quantization is typically something you do a lot in the framework, and there's nothing wrong about doing it in the framework. It's actually highly recommended. But if, let's say, you don't have the ability to do this, you've just been given a model and you want to compile it and you want to see if you just quantize it, change the data types to get faster performance on your hardware, then we can essentially apply quantization as a optimization pass in your compiler at compile time. And so there was this work done by my colleague Zihang at University of Washington, who essentially looked at your graph representation, inserted nodes to do simulated quantization. You could do some fine tuning of the scaling factors and do calibration. And then you could apply realization to turn this FP32 graph into an int8 or int32 compute graph. And that way you could target, edge devices that only can work on int8 types. So, taking all of this into account, I wanted to kind of touch on TVM and, what are the, what kind of results you can expect. So, I talked about code bloat, and for instance, just to revisit a previous example of showing, depthwise convolution, how hard it was to get really good performance there. So, just looking at the code base here, we have a depthwise convolution operator implementation. library, and in TVM it's about 700 lines of code. Now I'm not doing an apples to apples comparison. This is just kind of squinting, but in TVM this can cover all kernel sizes and data type implementation. So it's very powerful and takes a lot less code and can apply to a lot more architectures. And also, we've been getting very positive results, and here I'm comparing against TF Lite on a Raspberry Pi CPU on fairly mainstream models like MobileNets, SSD, object detectors, and PostNet, YOLO. Looking at TVM Untuned, which is the red bar, which is applying TVM, but not having done the automated auto tuning. As you can see out of the box, it doesn't always perform great. But then if you apply the auto tuner, which will do this automated exploration, you can get the performance to be a lot better. And then there's new work in the pipeline that is done by colleagues over at Berkeley and also who have interned at OctoML, which is this auto scheduler. It's kind of our next generation automated search over all the possible schedules that can be used to optimize a given operator, and this is producing even better results. So there's a lot of exciting work down the pipe, and with TVM, really you're getting this bespoke optimization for your one model running on your one piece of hardware. So that's if you really want to squeeze as much efficiency out of as possible. So the last talk and quick time check. I think I might be running a bit over time, so. Vijay, let me know what my time budget is to conclude. But I wanted to talk about microcontrollers because this class is really about TinyML. And I'm going to give you a very high-level view. And at the end of the lecture, I'll give you resources because it's very much work in progress. And we're working hard to get a solution out for people to use. But of course, I think it's a very interesting question to target microcontrollers because those are devices that are heavily constrained. There's typically very limited operating system layer. You have very stringent memory constraints. Typically, floating point is a no-go. Sometimes you have to actually use software implementations of floating point ops. And there's very limited machine learning runtimes and interpreters. Of course, TF Lite Micro is changing that and is offering a solution that is viable in many cases. And also there's very limited operator libraries. And I believe there's going to be a talk on CM/SysNN, which is a library by ARM in your lecture that tries to make up for that lack and can be used to target microcontrollers. And so just at a very high level, micro TVM is essentially TVM for microcontrollers. We wanted to essentially ask ourselves, like, how can we leverage this whole TVM stack and target these tiny edge devices and work around those constraints? So one of the first things we noticed, and when we started this research, we wanted to target RISC-V microcontrollers, was that RISC-V didn't have an LLVM compiler that was working at the time. Now that's not true. But so essentially we changed TVM so it could produce C code. And that C code, you could then hand it off to a cross compiler that would generate code for your targeted hardware. So it's a very simple idea, but it works really well because every different platform will have its own set of highly limited cross compilation tool chains. And we use the same trick to target the Azure Sphere, for instance. And then we have this micro device interface that's defined in our runtime to essentially read and write to device memory and control code execution. And with that, we have a fairly lightweight way to run and benchmark ML on the edge. This is necessary, as you can imagine, if you want to do auto tuning, right? So I'm going to go back on the Azure Sphere example from my colleague who had to work on this, very limiting device. And essentially, we had to figure out how to use TVM to target this Azure Sphere. He had this keyword spotting model. And as you can see, there's a lot of very common deep learning operations there that are composed of depth-wise convolutions and Bash norms and ReLUs, et cetera, that you need to run on this tiny little device. And so we just made the decision at the time to run the pre-processing layers on the Cortex-M4 and run the deep learning layers on the Cortex-A7. And of course, A7 is an application class core, but we could have, with TVM's flexible code generation, we could have chosen to also implement those layers on the M4. So thanks to the flexibility, we can make high-level system decisions on, what the best pipeline is to do some of this processing. And one of the things that made his life really easy was the out-of-the-box quantization. So he didn't have to take the model and bring it into a framework and maybe try to do some fine-tuning on data set. He could just get started really quickly on some experiments to apply quantization. In this case, we tried different approaches to quantizing the network. And on microcontrollers, oftentimes you're not really quantizing for just performance. You're just quantizing so that the model fits on the device, because the parameters are all on floating point and you can squeeze them into 8-bit representation, which will take a much lower footprint. So you're dealing with different types of constraints here. And so we looked at quantizing the whole network, leaving the first convolution layer out, and we try to make these trade-offs between accuracy and parameter size. Now, of course, you could recover that accuracy loss by retraining the model, but we didn't have much time to do this, so this is the best we could do in a few trials. This flexible optimization tool set made our lives quite a bit easier there. And finally, when we had the deployment and everything working, we added some auto tuning and got a bit better performance at the end from our default implementation. I think we could have gone a lot further. Microcontrollers have a fairly, or even low power processors have a fairly simple device architecture, so there's not a huge schedule space to explore. But we could have gone the extra mile by taking advantage of more low level optimizations, and we're working with ARM to get better sort of low level kernel intrinsic implementations added to TVM. So this is work in progress. But overall, we're able to achieve our target, which was to just get this, little proof of concept with TVM of a keyword spotting application on an Azure sphere. So here he's just demonstrating the system, and the LEDs are blinking in the right fashion. So, anyways, the thing was alive, and so micro TVM is a work in progress. There's a lot of exciting work and features ahead that OctoML is invested in. We're also working with partners like ARM to add some features there. One of the things that the community is excited about is ahead of time compilation, right? Just so giving you a really lightweight package to deploy on a microcontroller. This is something that we're doing in the Q4 horizon. Also, memory managers for RAM, flash, doing tensor pinning. We've been talking about also with our partners about accelerating some specialized accelerators like the Ethos U55 and doing heterogeneous runtime support. And also support for third-party libraries, right, like CMSysNN. Sometimes it's not really a question of TVM versus other libraries. We want to give people the best implementation as possible. And so we always want to offer the best of both worlds, right? So if CMSysNN does better on some layers, let's just use CMSysNN. So how can you sort of weave these different implementations and package that up into something that you can deploy on microcontrollers? That's a very interesting question. So that's it. We went over all these topics. And again, there's so much more to discuss on TVM, and I'm just giving you a quick snapshot. And I did not cover a lot of other topics, like how is TVM's runtime implemented? We have this really handy RPC communication mechanism to program and auto-tune edge devices. I haven't really talked about GPU support. I haven't talked about hardware supports and FPGAs, SPAR operator support, info quantization, et cetera. And also one of the things that is being worked on is also support for training workloads. And that's something I've completely left out here. I'm going to leave you with some resources on using TVM and getting yourself acquainted to TVM. I hope this talk has given you, has generated enough interest to maybe look a little closer at this project. And we also host yearly conferences on December 4th and 5th this year, and we'll have our third. So we're still a very young community. And this is where we're going to have more announcements around micro TVM. And this year is free and remote, so anyone can sign up and participate. Also wanted to talk about OctoML. So this talk has mostly been about TVM, and I didn't really touch on OctoML this much, but OctoML is a startup that I co-founded about a year ago, came out of mostly folks from University of Washington. And we essentially want to build an additional level of automation and optimization on top of TVM. So we wanted to bring this TVM goodness and add a layer of essentially of automation by packaging it into a service. And so you can imagine users saying like, hey, I have this model. I'm just going to drag and drop it. And I'm going to select from this drop-down box, oh, I want to deploy it on an Azure sphere. And then we're going to launch all the optimization necessary to then give you an artifact that you can deploy on your hardware of choice. And so it's been a very exciting, opportunity to take this research and work that has started in a university and take it, make it available to folks out there who could really use this to lower their data center expenditure, to increase efficiency on the edge, or just hardware vendors that want a software compilation story and that are dying for any means for people to use their hardware. I wanted to point out that we're hiring. We started about a year ago. We're 30 and growing. We're Seattle based, but we're open to remote. We got people on the East Coast as well. I've added a link for full-time positions, and we're also interested in hiring interns. And if you're taking this class, I'm sure you have a lot of really good tools to do well in industry. So please do feel free to reach out. And this is a photo of us just after we incorporated the company. There's 5 co-founders. I'm one of 5. And it was really, really exciting to start this. I'm going to leave you some resources that you can consult. There should be all on the slide, but I added some papers, tutorials, if you want to try those at home, some pointers on how to get started with micro TVM. Again, it's work in progress, so that's going to change a lot over the next 6 months. And link to our conference. And that's it. I'll be happy to take any questions now.
That's awesome. Love the talk. Thank you so much. There's a lot of fun, a lot of detail in there. That was super juicy. So that's good. I think one of the things that this talk does really well in class is that it actually gets into the meat of the stuff. As I said, like that's the point, right? There's a lot of voodoo that's happening beneath the hood that you typically don't think twice about, but that's really what makes or breaks. And yeah, increasingly, I think the TinyML space is really young, and as Thierry's pointing out, there's plenty of work to be done. In fact, Pete and I were just chatting. It's like one of the cool projects could very well be just, hey, take a bunch of these different frameworks and kind of like, just do a survey, right? There are not too many models that like these textbook kind of models that everyone supported, even if you just take AWS, right? And you can run through and understand like what are the differences you're getting and so forth. Anything you do in this space, you can actually stand out. It's that young. That does not come along too often, to be honest with you. Usually these areas are pretty seasoned, but TinyML, because I think of the resource constraints and everything, just kind of like, it's not something they can easily move into, so. And
I would love to see some TinyML perf work around this too. I think that would be really interesting, as we're putting together benchmarks. And maybe, I don't know if you've talked to Thierry about that at all, Vijay.
Yeah. We did touch base when we actually synced up and getting him over for this. Yeah, we did talk about it, and he was like, "Yeah, this would be right up the alley." So yeah, details on.
I love it. Yeah. No, I really loved all the work that's being done around ML perf. Actually, we started looking into this because we believe that having interacted, at least wearing my OctoML hat with a lot of hardware vendors, they're all looking for ways to benchmark their hardware in ML perf. But oftentimes they're looking for an entry point, right? And so you have your hardware, and does it mean you need to write a whole XLA backend or Glow backend or Onyx runtime execution provider? That's a significant engineering effort. Or you could use the shortcut with TVM and just get these models, use a standard compiler to target your hardware. To give you an example, AMD, for instance, they're known to make really good CPUs and GPUs. They're struggling to get into the ML market to some extent, at least in comparison to Intel and NVIDIA. And so, for instance, could you give them the ability to benchmark ML perf on a Windows laptop that has an AMD GPU via just the Vulkan drivers, right? So you don't need to build a specific compiler stack. You're just going to use Vulkan and give them the ability to get started and produce results. And so we're actually starting to look actively into ML perf, and that's something I'd love to talk at some point, maybe after this lecture. But just giving people a shortcut, a quick route to just getting these benchmarks done on hardware, even if you don't have compatibility with TensorFlow or some other frameworks to just get started, and just getting results within a day or two, as opposed to just putting out a ton of engineering, to do integration in ONX runtime or XLA, et cetera. So I think that's a really interesting opportunity. And really, I think the motivation behind TVM was also giving people a very clear view over, making rational hardware purchasing decisions, right? And with an uneven playing field in the software ecosystem, there's really a handful of vendors that really stand out. And everyone else, even if they have really capable hardware, they cannot make this hardware usable by others. And so if you have a compiler that kind of levels this playing field, then people can build much more interesting systems and make much more informed purchasing decisions or design decisions. I think that's kind of what's exciting.
Great. Yeah, other questions from the students?